Okay. Okay, welcome everyone to the second session of season 6 of the Isogeny Club. So it's our pleasure to welcome Laurane Marco at the Isogeny Club, who will be talking about computing modular polynomials modulo a generic prime. So the floor is yours.
Thank you. So thank you, Maria and Jonathan, for the invitation, as always. So today I'm going to talk about modular polynomials and how to compute them. And this is work that I did while I was visiting Stephen Galbraith at the University of Auckland. So despite the fact that there's the PFL logo everywhere, it's actually work that was done when I was in Auckland. All right, so wait, I can't. No, okay, there you go. Sorry. So what are modular polynomials? So we denote the L's modular polynomial by phi sub L of xy. We know that it's a bivariate polynomial. It has integer coefficients. It has degree L plus 1 in both variables. It is a symmetric polynomial. And it has this very nice property that when you give it as input two J invariants J and J primes, then it evaluates to 0 if and only if there's an isogeny phi between two elliptic curves E and E prime, with J invariants respectively J and J prime, and the degree of this isogeny phi is L precisely. So it's a really nice property. And what do these polynomials look like? So for example, this is phi 2 of xy. So this is taken from database by Andrew Sutherland. And you can already see that phi 2 is quite a big polynomial, like the coefficients are kind of growing quite a bit. So you can kind of imagine that if you go to like bigger values of L, then it's going to be quite hard to write down. And in fact, the total size of phi L for general L is of the order of L cubed log L. Okay, so why do we even care about modular polynomials? So the main application is for point counting on elliptic curves. So they're used in the algorithm that's used for point counting. But this is the Isogeny Club, right? So we're also interested in applications to isogeny-based cryptography. They're used in some protocols, mainly the CRS key exchange and OSIDE, and they're also sometimes used in like some very niche subroutines and some other isogeny stuff. Sometimes like when you read some papers, they pop up here and there. And in our case, Stephen Galbraith that I worked with on this project also used them in his paper recently, Climbing and Descending Tall Volcanoes at Ants, and that's kind of how he got interested in the subject, also with the fact that he actually saw a talk by Sabrina Kunzweiler and Damien Robert at Ants as well, and I'm going to talk about this more a bit later, about specifically computing modular polynomials. So what are the challenges when it comes to modular polynomials? So there are four main tasks that we can consider. The first one is, well, just computing your modular polynomial over the integers. The best algorithm that you can kind of hope for is of the order O of L cubed log L, which consists just in like writing down your polynomial kind of takes that amount of work. So that's kind of the best that you can hope for. Then the second task, which is closely related to the first one, is computing your modular polynomial modulo a prime p that you choose. So you don't have the choice over L, but you can choose a prime p, and then you're asked to compute phi L mod p. And a very similar task, which is the third one, is the exact same thing, but this time you don't have the choice over your prime p. So you're given L and p, and you're asked to compute phi L mod p. And for kind of both of these, you can kind of hope to go at best for something of the order of L squared log p. And then the final task, which is worth mentioning, but that we won't really talk about more in this talk, is how to like evaluate modular polynomials. And in this case, the best complexity that you can hope for is of the order of L log p. So for the remainder of this talk, I'm going to talk a little bit about the first one because it's kind of important in the literature, and then we're going to focus on the third task, which is going to be kind of what we worked on precisely. So you'll see it's kind of still a bit of work in progress, sort of. I'm going to try and kind of walk you through like our reasoning and how we like the challenges that we faced here and there when we're like going through the project, and hopefully you'll gain some, I don't know, some educational insights as we go through the talk. All right, so let me start with the beginning of the story about computing modular polynomials. So the main challenge is that they're really big, right? And so the first algorithm was main algorithm was by Brocker, Lauder, and Thurderland, and they used isogeny volcanoes to compute modular polynomials for prime level L. So kind of now it makes also a bit more sense as to why we're talking about it in the Isogeny Club, right? Computing modular polynomials also uses tools that come from like isogeny-based cryptography and stuff in general. So their general blueprint is the following. You kind of start by choosing a set of suitable primes P. How you choose them kind of depends on the algorithm that you're going to use for the second step, which is you're going to compute your modulo polynomials modulo these special primes P. And then once you've computed them for enough P, you apply the Chinese remainder theorem, and then you recover your modulo polynomial over the integers. And as far as I know, I think these kind of general strategies reused in all subsequent works that attempt to compute modular polynomials. So we're going to kind of go back to this strategy quite a few times throughout the talk. So how do they do it? At the very, very high level, the idea is like you map out some well-chosen isogeny volcanoes. So by doing so, you're going to collect some relations between J invariants, between curves and their respective J invariants. And then you're going to use this knowledge to interpolate your modulo polynomials, and then you're going to recover it during CRT. So if we look a little bit more in details, you're going to start by choosing an order O, which is going to correspond to like the endomorphism ring of your curves. And you want this to have a big class number so that you have enough surface on your isogeny volcano. So we're dealing with ordinary elliptic curves here. And then you're going to choose a prime P to ensure that your volcano is going to have depth 1. And then you start from a J invariant J0 that you compute using, you know, like the Hilbert polynomial, whatever, but the details are not too important here. So you start from the J invariant J0, and then you use the action of the class group of your order O to enumerate all the curves on the surface of your volcanoes, and you collect the J invariants along the way. And once you've enumerated the entire surface, you need to go down, you compute a descending isogeny using Vellu's formula, and then you kind of do the exact same thing on the floor, and you use the class group action of O prime, which is kind of the orders to which the endomorphism ring of the curves on the floor are isomorphic too. So basically you kind of do the same thing on the floor, you collect all the J invariants, and then you kind of have the relationships between all the curves that are in the volcanoes. And you do that and map up like all the volcanoes that make up these elliptic curves with endomorphism ring O over FP union, the same thing with O prime. And once you know the relationships, you've collected enough J invariants, and you can interpolate your modular polynomial from its roots, and you repeat it for enough values of P. And then once you've recovered phi L mod P for enough P, you can just kind of use the Chinese remainder theorem and recover it over the integers. All right, so I guess this is probably like nice for people who are familiar with isogeny volcanoes and ordinary elliptic curves, but maybe if you do isogeny-based cryptography, it's not your cup of tea. So then, well, I'm kind of extrapolating a little bit, but I think then Antonin came up with the new technique to compute modular polynomials, and you know the idea was like kind of isogeny-based cryptography actually has a lot of tools for supersingular elliptic curves. So what about we use supersingular elliptic curves instead, and how, like, what can we do with it? So this is from his paper, computation of Hilbert class polynomials and modular polynomials from supersingular elliptic curves. So here the idea is that you're gonna choose a prime P to have enough supersingular elliptic curves over FP square. you're going to gather a good set of maximal orders. So you're implicitly using the Turing correspondence here. So you compute a set of L+1 order in your quaternion algebra. And then from each of your orders, you compute L+1 left ideals of norm L, which are going to kind of correspond to L isogenies. And you also collect the orders at which they arrive. And then you get a set of L+1 orders of different types. This is to ensure that you have also different J invariants in the end. And then you start from a starting curve with known endomorphism ring. So that is isomorphic to some order O0. And then for each order in your set, you compute the connecting ideal, you compute an equivalence smooth ideal, translate it into an isogeny, collect the J invariant of the image curve, and so on. And then you've collected all of your J invariants, and you can again interpolate and again repeat it for enough primes, and then use the Chinese remainder theorem to recover your modular polynomial. All right, so now we went from ordinary elliptic curves and isogeny volcanoes to super singular elliptic curves and the Turing correspondence. And then isogeny-based cryptography kept developing new tools, and namely the, like all these high-dimensional isogenies and all of that. And this leads us to the approach by Sabrina Kunzweiler and Damien Robert, where they started using the new HD toolbox. So I'll add a disclaimer here. I think like this is not the stuff that I'm most familiar with, so I'm gonna try and give like a brief overview of what they did, and like I hope I don't say anything that's wrong, but this is kind of like what I got out of their paper. So they kind of used THD representations to compute a set of L+1 J invariants at the beginning. And then they used something called higher order deformation, which I tried really hard to understand, but didn't really, to compute everything else that they need. And then this allows them to compute phi L mod P for a P that they choose and that is nice enough. And then again, they use the exact same technique of using the Chinese remainder theorem to compute it over the integers. But at some point in their paper, there's a remark that sketches a method to compute modular polynomials for generic prime P. And this is kind of what caught our eye with Stephen when we're looking at their work. So you start from an elliptic curve E0 with known endomorphism ring. And then you use Clapeyron to compute all the L+1 outgoing L isogenies. And this is kind of nice because it removes some heuristics from previous work that depended on the general Riemann hypothesis and all of that. And apparently you can do this in complexity sub O of log L plus log P for some constant, I never know how to pronounce this later, frac O that is independent from P and L. So this is quite nice. And then they don't really specify how you keep going, but I would assume that they kind of use their deformation method again to recover the remaining J invariants. So that kind of got us interesting. So they have this like blueprint for doing this, and we're like, okay, but so in this context of generic prime P, like what can we do? In some applications, it's not reasonable to assume that we can control the prime and we can choose which prime. So what is the cost that we pay on complexity in this setting? So for the rest of the talk, our task is going to be to compute phi L mod P for any primes L and P that are co-prime to each other. So as a reminder, as I said, the best algorithm that we could hope for would be of the order O of L squared log P. And the blueprint for algorithm is going to be very similar to everything that's been done before. So you start from some special curve E0. You compute L+1 isogenies of degree L in some way. You collect the corresponding J invariants. You kind of move this work around to like collect the remaining J invariants, and then you interpolate to recover it mod P. So how do we do the first step? So from a given starting curve, we want to compute all the outgoing L isogenies. So previously it was done either like you kind of knew the target curve somehow, you compute the connecting ideal, you do the ideal to isogeny computation, and then you get the image curve and it's J-invariant in the case of the work that was done by Antonin Leroux. And in the case of the work by Sabrina and Damien Robert, it was just using Clapauty. So our idea was we start from a curve E0 of known endomorphism ring, and then we use this very popular technique in isogeny-based cryptography that was introduced in QFESTA by Nakagawa and Onuki to compute kind of or L isogeny by factoring out an endomorphism. So let me give a little reminder on the QFESTA technique. So you start from a curve E0 of known endomorphism ring that we denote O0. You have a prime P, an integer D that is smooth that divides P minus 1, and another integer that we denote L in our case. That's going to be the degree of the target isogeny. And we want to compute an isogeny phi from E0 to some curve E that we don't really know, but we want phi to be of degree L. And so how do you do it? You sample an endomorphism theta in your endomorphism ring, which you can do because you know the endomorphism ring of norm L times D minus L using the full represent integer algorithm that was introduced in KLPT and refined in the ski sign papers and the follow-ups. Then you write your endomorphism theta as a product of two isogenies psi and phi, with phi going from E0 to E of degree L. And I'm now noticing that it's not consistent with the diagram on the right, so you can just ignore that. And then psi from E to E0 of degree D minus L. And phi, little phi is going to be your isogeny of interest. And then from this, you give rise to a two-dimensional isogeny phi of degree D, whose kernel is given by all the points LP and theta P for P in the D torsion of E0. And then you can evaluate your little isogeny phi, your L isogeny that you're interested in, as big phi evaluated on P and 0, and you can kind of recover the image curve as well. So how do we use it in our context? So you compute endomorphism of degree L times D minus L. You compute the codomain of the L isogeny, and it's J invariant. And you kind of repeat these steps until you've collected enough J invariants. So the good thing is that computing high-dimensional isogenies is pretty efficient these days, and I think there's a lot of research going on, and it gets more and more efficient by the day. But the downside is like by doing so, you kind of generate sort of random endomorphisms and you don't really have a lot of control over it. And you potentially have a lot of redundancy until you collect L+1 different J invariants. So at this stage, we're like, okay, what can we do to kind of have a bit more control and maybe decrease the redundancy? So we started with this observation that, okay, suppose you have an endomorphism theta in your endomorphism ring and you know basis of the order O0 given by alpha 1, alpha 2, alpha 3, alpha 4. I see that there's something in the chat, but I can't really read it, so just interrupt me if it's anything important.
There's a question from Frey.
Okay.
If P is random, how can P minus 1 be smooth?
Okay, that's a good question. This is kind of in the setting that was just for the sake of explaining QFESTA. And in generality, we don't assume this, and we just have to like deal with arithmetic over extension field and ugly stuff. I hope that answers the question. Okay.
Yeah.
What was I saying? Right. So then you can write your endomorphism theta as like a linear combination of your basis endomorphisms. And if you assume that you have a basis for the L torsion as well, you could also write the action of the basis of the alpha I on the L torsion as matrices AI. And if you know the kernel of your endomorphism phi, then it verifies this equation here. So the sum of the alpha AI evaluated at k is 0 mod L. So this gives you a very nice, like, simple equation. And you can be like, okay, so maybe instead I can kind of like choose the kernel somehow and then derive the coefficients accordingly. But then if you do this, you kind of have no control over the norm of the endomorphisms that you generate, and that's not good for our purpose. So then we're like, okay, so what about we incorporate this equation into the norm constraint somehow? So we want to verify these two things at the same time. And we're like, okay, so like, how do we generate endomorphisms of a given norm? It's using this like represent integer or full represent integer algorithm. So what would it look like? So you sample the last two coefficient, lambda 3 and lambda 4 at random. Then you set m to be 4, and the 4 comes from the full version of represent integer minus p times lambda 3 squared plus lambda 4 squared. And usually you would just solve x squared plus y squared equal n using Kronecker algorithm and call it a day. But in this case, you try and incorporate the equation that you have above, and then you get some very ugly quadratic form with big coefficients. And at this stage, we kind of gave up and were like, okay, there's no way we can solve this, and scratched this approach. So that was another dead end. So then we're like, okay, what if we use endomorphisms that are a bit nicer to deal with, then we restrict ourselves to Zi. And if we have endomorphism of the form lambda 1 plus I lambda 2, is it easier to control? And maybe people watching already know the answer, but it took us slightly too long to realize. So you choose now a value d such that L times d minus L is representable as a sum of two squares. And then you compute the values x and y such that x squared plus y squared is equal to L times d minus L. And you have several values because a priori this number is composite and not prime. And then you get that the kernel of your isogeny, of your L isogeny phi, is given by the intersection of the kernel of your endomorphism x plus iy with the L torsion. And you want to look at solutions of x squared plus y squared is 0 mod L that come from the solution of that we had above, right? Of x squared plus y squared is equal L times d minus L. And that means that you must have y over x squared to be minus 1 mod L, and then you can only ever hope to have two possible values. And this is also independent of the value d. So even though you change the value d, which changes the norm a priori of your endomorphism x plus iy, you're only ever gonna get two L isogenies ever. And when you're trying to get L plus 1, it's not good. And so you can't restrict yourself to this case, and you had to scratch that as well. So this was kind of more of an educational side way. All right, so where do we stand now? So our overall strategy was, okay, we compute endomorphism like this, of degree L times d minus L. For each, we compute the codomain of the L isogeny and its chain variant, and we repeat it until we've got enough. And we really haven't found any good ways of controlling the endomorphisms. So we kind of had to settle for using this condition as kind of a check before executing step 2. So instead of like collecting the endomorphism, doing this high dimensional computation and so on, we just used this kind of like linear algebra step to check that we get different L isogenies. So let me go over the details. So you compute your endomorphism theta. Then you compute the kernel of the linear combination sum of lambda I AI. So recall that these matrix AI correspond to the action of the basis endomorphism on the L torsion. So this gives you the kernel of the corresponding L isogeny, and if you've seen it before, you discard it. Otherwise, you kind of like keep it in track, compute the corresponding L isogenies. It's using the high-dimensional tools, the image curve, and the corresponding J invariant. And you repeat it again until you've collected enough J invariants. So really here, the trade-off is like, okay, instead of doing the expensive, I guess, in comparison, high-dimensional computation every time, you just do this step before. Nice. And then, oops.
Chat. Sorry, just to interrupt you. There's a question in the chat on are there any constraints on D?
On, sorry, what?
On D, on like this integer D.
I guess you want it to be like power smooth and as nice as possible, because this is kind of like this is going to be the high-dimensional isogeny that you're going to have to compute, right? But a priori, otherwise, no. All right. So now we've collected all the kind of like the first set of J invariants. So we have the starting curve E0 of J invariant J0. We've computed all of its L isogenous neighbors and their associated J invariants. And then you can interpolate phi L J0Y from its roots. But if you want to compute phi L of xy fully, you kind of need to repeat this collection step more times to kind of be able to interpolate the full modular polynomial, mod p every time. Sorry, I forgot to write it. So should we repeat our previous strategy, or can we do something else? So we kind of, it's a bit annoying because you need to start with the curve of known endomorphism ring, and you have some other costly stuff going on, like actually computing the basis for the L torsion and so on. So we would ideally want to reuse the work that's already been done. So here the idea was to kind of push the information that we have around. So we have E0 and we have all the curves EI that are L isogenous to E0. And now we're going to suppose that we have some more information. So that we have, for example, a basis of the D torsion for some small prime D coprime to L, and also the image of P0 and Q0 through the L isogeny. So we denote PI, QI, the image of P0, Q0 on the curve EI that is L isogenous to E0. And then the idea is going to be for each of the curve E0 and EI, and all of the EI, to compute all possible D isogenies. And collect, so you're going to have kind of, let's say E0 and E1 are L isogenous, and then you compute a D isogeny from E0, and you compute the same D isogeny from EI in SIGH style, and then the image curves are going to be L isogenous again, and you're going to collect the curves and their J invariants, and you're going to repeat that again until you've gathered enough J invariants. Again. All right. And then you get phi L of J I Y for enough Ji's, and then you can interpolate your full modular polynomial, phi L x y mod p. Okay, so let me summarize everything that we've discussed so far. So given two primes L and P, you pick a starting curve of a known endomorphism ring, and you do the following steps. You pick the power smooth ideally, and you construct endomorphisms of degree L times D minus L using the full represent integer algorithm. You compute the kernels of the L isogenies using the linear algebra trick. If you haven't seen it before, you collect the endomorphism. You repeat it until you have L plus one good endomorphism somehow. And then you compute the J invariant that corresponds to the image curve of the L isogeny using the QFESTA trick, the QFESTA technique. Then you push all this information around, and then you use all the J invariants that you've collected to interpolate your modular polynomial. So what is the complexity of everything? So the first step, which is just computing an endomorphism of a given norm, you can do it using the full represent integer algorithm, which runs in time polynomial and log of the input norm. So here maybe like a little call for help is, I don't know if anyone has ever looked into the actual concrete complexity of this algorithm, but I've kind of looked at several places, and this is kind of the most precise statement that I could get. So happy to discuss that if needed. And in our case, n is going to be of about O of p, so the complexity is going to be polynomial in log p. For the second step, computing the kernel of the L isogeny somehow using the linear algebra trick, we can kind of decompose it in three subtasks. So you need to compute a basis of the L torsion on E0. You need to compute the matrices that correspond to the action of the basis of your endomorphism ring on the L torsion. And then you need to compute the kernel of this matrix. So looking at these, the first two tasks are going to be the most costly, and especially the first one. But kind of the idea here is that you can do it once and for all per choice of L, and you don't need to redo the work every time you have a new endomorphism. So the dominating cost is going to be really the first step. So your L torsion basis, because you have no control over P, is going to be defined over some extension, some field extension. Then you can show that the size of this extension is going to be at most L minus 1. So you're going to get that your complexity is going to be log P plus log L times the complexity of doing arithmetic over your field extension. And for the second step, it's going to be about solving what I call a double discrete logarithm. I know this isn't how you should call it, but I don't know what's the correct word for it. And you do it quite a lot in isogeny-based protocol, and it's sort of efficient in practice, especially compared to the first step. And then the third part is going to be just like matrix operations for some two-dimensional matrices. So it's going to be very efficient. All right. Then we need to repeat this until we've collected enough endomorphisms and then do the HD computation. So assuming that the endomorphisms that full represent integers output are sort of random, you need to repeat it about O of L log L times. So we've kind of tested that in practice, and our experiments matches this estimate. And then you need to compute your L plus 1 higher dimensional isogenies. So you compute a D isogeny, you decompose dr, this should be a product and not a sum. I'm so sorry about that. As a product of, you decompose D into its prime product, so pi to the power ei. And then you have a result by Damien Robert that tells you that you can actually do this computation in polynomial time, but the exact complexity kind of depends on the degree of a bound of the degree of the extension of the pi to the ei torsions and the piei times pjej torsions, as well as the biggest prime factor pi. So we haven't worked out explicit bounds in our case, but this is kind of gives you an intuition. Then you need to do these pushing curves around a step. So for each small prime degree di, you're going to have to compute all di+1 outgoing isogenies for each of the L+2 curves that you have using Wheeler's formulae. And you repeat that enough times such that the product of the di+1 is greater than L. So if we say that, if we consider d max to be the biggest degree that we're going to have to compute, our total complexity is going to be about stuffed O of L squared of square root of this maximum degree. And we can estimate it to be roughly the log L prime. So we're gonna have something of the order of log L log L. So this gives us a total complexity of the order of L squared square root of log L log L. Nice. And then the final step, which is just the interpolation step. This is just standard. And the complexity comes from the paper by Broker, Lauder, and Sutherland. And it's going to be O of L squared almost log L squared almost log P somehow. And so overall, in our context, we're going to have one very expensive one-time pre-computation of the L torsion basis, which is going to be of the order O of log P. I don't know why there's a square, plus log L times the cost of your arithmetic of your over your extension field of degree at most L+1. And then you're also going to have to compute these like smooth torsion bases for pushing curves around, but this is going to be for very small primes, and in comparison, it's going to be negligible compared to the cost of computing the L torsion bases. Then you're going to have to collect all your nice endomorphism, which can be done using full represented integers in time polynomial in log P, and you're going to have to repeat it L log L times. Then you're going to have to do these higher dimensional computations, which you're going to repeat L+1 times. And then the rest of the formula is kind of ugly. But basically, the i's are the coefficients. Then you're going to have log P squared that comes from the base field, which is over FP squared. And then the D1 and B1 should be the norms over the field extensions that I mentioned a couple slides ago. And then you're going to have to push your curves around, which can be done if in O of L squared square root of log L log L. And then you interpolate. All right. So to discuss this, so we're kind of far from a rigorous approach. We have heuristics hiding a bit everywhere. It's hard to compare with the approach by Sarah Kunzweiler and Damien Robert because they only sketch it. And I mean, like, her approach is also kind of more at the, I guess, not fully worked out yet. Maybe it's better than what Antonin has, or maybe not. We played around a little bit with the implementations, but we're lacking the tools to compute the corresponding high-dimensional isogenies. And we also have to deal with the arithmetic over extension fields, which is not really nice. And I guess like implementation isn't really my forte, so any help would be appreciated if you're interested in it. And also any insights are welcome on everything that's been said so far. And this is it for me, so thank you for your attention.
Thank you very much for the talk, Laurane.
Thank you.
If there are questions, please type them in the chat or just unmute and ask them. So there was one question by Pierre during the talk, which was, since you're already working with the kernel points, do you really need a two-dimensional framework? And asking if you can maybe just use Wheeler's formulas instead to get the L+1 isogenous chain variant.
Honestly, I think we started by wanting to use this framework and we kind of went like tunnel vision into this. So maybe actually this is just better and we should look into this. Yeah, I guess, like sometimes we just go like full on and yeah. So possibly, I don't know. Yeah. I got a little bit scarred by this project.
Can I ask, just can you remind me what you needed the L torsion for again?
So the idea is like before you compute these like HD isogenies, you want to do this check to see if the L isogenies that you get from your endomorphism is nice or if you've seen it before, sort of. And to do so, you use this check that requires to know the action of the basis endomorphism on the L torsion. And so you kind of need to compute the basis of the L torsion in the first place. Does that answer your question or no?
Yeah, it does. So then in that case, I'm not sure if this is really true, but maybe it's worth checking out. I'm not sure if you really need to compute a basis of the L torsion to do this because like what as I said, this is really guessing, so not sure. But you can fix an isomorphism to the order modulo L, and then take the endomorphism you have seen, push it through this isomorphism, and then well, the order modulo L, it looks like two by two matrices. So then, and since its norm is L, it's gonna have a kernel. And somehow it feels like maybe you can bypass this check going via curves and just directly look at the kernel.
Yeah, that's actually
in
really
this sense.
interesting. Yeah, because I think this is really the main
Maybe.
bottleneck, like this very expensive like pre-computation. So if what you say is true, then maybe it could be interesting to look into it. Yeah.
Maybe worth checking. Yeah, there's an algorithm by Voigt that so that's a bit more explicit somehow, but that computes all ideals of norm L, and this kind of uses this isomorphism and yeah.
Cool. Yeah. Well,
So
if you
maybe it's worth
send me
checking
the
out.
reference, I'll be happy to read it.
There's another question in the chat. So does the size of the endomorphism matter, as in the size of its norm?
I guess, I mean, if you want to use the QFESTA trick to then compute the isogenies, then you want it to have a special shape. So yes. If you're going for, I don't know, a different way of computing your isogenies, then like, I mean, this is kind of a whole different algorithm. I guess yes, the answer is yes in your context. Yes.
On that question, I remember, but maybe I'm remembering wrong, that you said you fix D and then you compute the endomorphisms. But couldn't you like just vary D and just choose different D for each endomorphism as long as it's like somewhat smooth? It doesn't really.
Yeah, we played around with that as well, kind of, yeah. And the like kind of more practical implementation, I want to say. But we don't have a full working implementation because, yeah, as I think I saw some comments in the chat, like anything other than two isogenies is not really a thing yet.
Yeah.
There is tons of little tricks like that that you can try, but it's kind of hard to assess the concrete impact on the overall algorithm since you don't really have a working overall algorithm.
Yeah. Yeah, I guess you would hope that you could find these endomorphisms faster or something.
Yeah.
Maybe it's unclear how much it actually matters.
Yeah.
Are there any other questions? Okay, if not, I'll let's thank Laurane again And yeah, I'll stop the recording.